Okay, so day 12 here, and it actually hasn't started yet, but I just wanted to. Someone sent me this link of the thing I couldn't figure out yesterday, where you had to compute basically every possible square efficiently, and I didn't do it efficiently. But there's a summed area table that I did not know about. But basically, you pre-compute every possible sum of a rectangle from the top left, and then using that. You can basically get any rectangle and hence any square by just using 4 of your pre-computed values, which it's pretty neat, and it would have been cool if I'd invented that myself last night, but I didn't. So what are you gonna do? So let us look at problem 12, subterranean sustainability. Okay, so let us. Day 12, subterranean, what was it called? Sustainability. Never going to get a high score if I waste all my time naming things properly, but that's okay. The year 518 is significantly more underground than history books implied, or even implied vast cavern network. After exploring a little, you see a long tunnel, a row of small pots left and right. Few of them contain plants. Someone is trying to grow things. Pots are numbered with 0 in front of you. To the left, the pots are numbered -1, -2, -3. To the right, 1, 2, 3. Your puzzle input contains a list of pots from 0 to the right, and whether they do or do not contain a plant. The initial state. No other pots currently contain plants. For instance, initial state of pound 0, 1, 2, 3, 4 currently contain plants. But also needs some notes. You find someone has been trying to figure out how these plants spread to nearby pots based on the notes for each generation. Human pot has or does not have a plant based on whether that pot and the 2 pots either side of it had a plant in the last generation. These are written as LLCRR, where and N is where the current bottom of the plot. So a note like this means a pot that contains a plant but with no plants within 2 pots of it will not have a plant in it during the next generation. A note like that means that an empty pot with 2 plants will have. Like that means if a pot has a plant in a given generation. If in the previous generation there were plants in that pot, the one immediately to the left, the one 2 pots to the right, but not the ones immediately to the right. It's not quite expensive for it. Sure, it's important. Making sure the current variation of plants is sustainable, determining what will happen after 20 generations. For example, given the following input and the initial state, for brevity in this example, only the combinations which do produce a plant are listed. Your input includes all possible combinations. Then the next 20 generations will look like this. Generation blah blah blah, blah blah blah, blah blah blah. After one generation, only 7 plants remain. The one pot 0 much, and so on and so forth. Adding up the numbers of plant containing pots after the 20th generation produces 325. After 20 generations, what is the sum of the numbers of all pots that contain a plant? Okay, so we can probably do this. So I am going to, and this may be a terrible idea, but I am going to use a set for this. And so we will say a state is just a set of ints, and a rule is also so let's call this -1, -2, -1, so 5, and so let's say a rule is a tuple of int, and it's possible I'm going to totally regret this representation, but that's fine. And we'll say that the rules is just a set of rule, and actually no, I don't. This is a tuple of booleans, bool. Okay, and so I think this is good. So let me see what the input looks like, and we'll figure out how we're going to parse it. And so let's do this. And here we have, okay, so that's good. So let's say raw equals this. And let's just do split on new lines. And regex equals initial state like that. We will import regular expressions. And now what we'll do, and actually, you know what, rather than do that, let me just write a function that parses all this, because I'm going to need to do this on our inputs anyway. Parse raw, which is a string, and it's going to return two things. It's going to return a state and some rules. And so what I want to do is the following, and I want to say lines equals raw.split on new lines, and so let's say initial state equals re dot match regex lines 0 dot group. We'll see if that's even right. It might not be. And then what I want to say is rules is going to be a set, and for line in lines, so I'm going to skip this blank line and start in 2. And now let's get a new regex, which is 1, 2, 3, 4, 5 space equals over to the side, and then this, and let's say pattern plant equals re.match line regex line dot groups. And now what I'm going to say is if plant is turned on, which is I think what they said, right? If plant is turned on, then the key is just tuple of, what do I want to call it? C equals blank for C in pattern, and rules dot add key, and then I want to return initial state a rule. But actually this is not what I want for the initial state. So this is really like initial state raw, and then initial state equals I for I plant in enumerate initial state raw, if plant is this guy. So there's no way that will work on my first try, but let's try it. D12, parse raw. So this is definitely not right. So let me do this just to make sure. Line is this, and somehow this group thing is not right. So let me do this. Regex re.match regex common line dot group. That's not right. Dot groups 0. Okay, so that's what I wanted. Dot groups 0. So let me try this again. Run this and then parse the raw. Now it says 0, 3, 5, 6, 7, 8, 9, and so on. So that looks good. And then we have that, and that looks good too. And so now what I want to do is I want to step, so let's say state and rules, which is going to be rules, and that's going to return a new state. And so what I want to do is the following. For plant in state, key equals tuple of, and again, what I want to do is basically other in state for other in plant -2, plant -1, and plant +1, plant +2. So I'm basically just saying which of those are turned on, and let's say next state equals set for plant in state. Oh, but actually that's not right, because we basically have to look at every, so this is where the inefficiency is going to come in. But basically, hi. Okay, we'll just trade for the week, okay? Okay. Okay, sorry. Kid issues. So what I need to do now is let's just try this in a naive way and say say low equals min of state -2, high equals max of state +2, and then for plant in range low, high +1, key equals this, and now if key in rules, then next state dot add plants. Okay, so so let's do initial state rules equals parse raw, or let me just do that. So let me run this thing again. This is hard to tuple other in state for other in this. So I left off another brace. So let's run this, and let's say state step state rules, and I probably need to return next state. So let me run it again. So after 0, 3, 5, it goes 0, 4, 9, 15, 0, 4, 9, 15, 18, 21, and 24. And then it goes 0, 1, 4, 0, 1, 4, 5. Okay, so it looks like that's doing the right thing. And so now this is saying the next 20 generations will look like this. So after 20 generations, so def count plants, and let's say initial, which is a state, rules, which is a rules, and num generations, which is an int, and this is going to return an int. And so just call this state. And so let's say for blank in range num generations, state equals step state comma rules, and then we want to return the sum of the number of all pots which contain a plant. So that would just be sum of the state. And so now let's run this. Count plants of what I call it state rules 20, and that says 325, and that is right. So now let's get our input, and so let us do this day12.text, and that's good. So hi everybody. So now let me just add a unit test. Assert count plants of state rules and 20 equals, and what did I say, 325? Okay, so now with open data day12.text as f, raw equals f.read, and now I can again say state rules equals parse raw, and how many generations do I need to go? Again, 20 generations. So print count plants state rules 20. Okay, so let us run this. None type has no attribute groups. So did I get a bad line? Is there just an empty line at the there's an empty line at the end. So let me ref.read.strip. So let me do that, and I think that will fix it. Okay, and this says it's 2349. So it worked the first time. So after 20 generations, what is the sum of all 2349? That's the right answer. 1 gold star, 159 on the stars leaderboard. Continue part 2. You realize that 20 generations aren't enough. After all, these plants will need to last another 1,500 years to even reach your timeline, not to mention your future. After 50 billion generations, what is the sum of all pots which contain a plant? Okay. Presumably that means there's a pattern here. And so like, I'm not going to run this for 50 billion generations, but my guess is that at some point it's going to hit the same state twice, and then if that's the case, it will cycle through again, so let me do scene equals set, and then while true, and scene won't be a set, scene will be a dictionary that is going to be all plants to generation number. So again, let's see, do key equals, and we'll do tuple, so we make it a key, and then we'll do sorted state. So we're going to, and let's say generation equals 0. If key in scene, print generation scene key, or I'll just do this. scene key comma generation, and I could be off base here and break otherwise scene key equals generation, and then generation plus equals 1. So if I run this, we'll see what happens. Okay, well, it stopped immediately, so that's not good. Okay, print generation scene. Okay, and did I not? I did not step. And then so let's do state equals step state comma rules generation plus equals 1. Okay, so that's more what I wanted to do. And so that doesn't seem great either because it's running for a long time. So let's go back, and rather than doing this, print. So let me say from itertools import count. So count will just let me count however. So for I in count, print state, or print I comma state, and then state equals step state rules. So let's actually, you know what? I'm not even going to do this. I'll say I'll do it 1,000 times and see if we can see a pattern. So let's see how many are active, because it looks like it's drifting. And so 42, 42, 42, 42, 42, 42, 42, 42, 42, 42, 42. So another possibility is that, and lens state, sorted state. So this could be one of those where you're using outside the system. So so let's look at this where I can get to. So 0, 1, 6, 1, 5, 6, 0, 2, 3, minus 1, 0, 2, minus 1, blah, blah, blah. So let's look for one where it looks like 0, 1, 6. So you know, let me go back and get this thing back. And I'm just undoing. Okay, so now I'm going to be a little bit more clever about, so let's say lowest equals min state, key equals tuple, and so let's say deltas equals plant minus lowest for plant in state, key equals tuple of sorted deltas. So now what we're doing is if key and scene print and so I want to do generation number comma lowest. So and let me call this deltas goes to generation number and lowest. So we have this key, if key is scene, print scene key, otherwise scene key equals generation comma lowest, step generation equals +1. So now let me try this and see if this works. Okay, So let's figure this math out. What did I print? Scene, key, generation. So this says that at 184, so let me do this. Print generation and let me do this. Print generation and key. So let's do that. And what we say is once we get to 184 and 185, they have the same. So print generation, lowest and key. Okay, so 184 is the lowest is 141 and it has the same pattern. 185, the lowest is 142 and it has that same pattern. Lowest key, and then sum of, let me do sum of state. And so we're just going to find the pattern, sum of state. Do that, and this says 8896, 8938. And let me just, rather than doing while true, I'm going to do for generation in range. Let's just do 200 and make sure that the pattern works. So let's run this. And so it adds 42 at every time step afterwards, right? So once I get to so let's let me just do 201. So at 201, so after 200 generations, I get 9568, and I said it adds 42 at every time step, right? So, and maybe that's the key observation, that what I have is 9568 plus 42 times, how many do I have left? 2 billion. How many did it say? 50 billion. So let's do that. What is the sum of the number of all plants that contain a plant? So let me just do this. 50 billion minus 200, right? So in the first 200, I get up to 9568, and then I've said that I'm going to get another 42 every single one that's left. So if I do that, it's going to give me this giant number. So let us try that and see if it works. That is the right answer. You are 1 gold star closer to fixing the time stream. And once again, we ended up in the top 100 and gained some points, which is fantastic because that rarely happens. Great. So I do think fast, but this is like the 3rd year that I've done Advent of Code. And so one thing that I've learned from doing Advent of Code for 3 years is that when they give you something that's plainly untractable to run, like figure out what happens after 50 billion steps, you simply can't run it for 50 billion steps. So there must be a pattern there that they're expecting you to find, because that's the only way that the problem could possibly be solved. And so there's something that's kind of really, in some sense, unsatisfying about that, in that you have not solved this problem generally. You've solved it in a way that works for this particular input, which happens to have a pattern in it, but you have not solved it generally. And so that's a little bit disappointing. But the key thing is just this, this understanding that, and this is a little bit unfortunate because my code doesn't really reflect exactly how we solved it. So I'll just put a comment in here that there's going to be a pattern here. And so as you saw, my first idea was I'll just look for a state that repeats itself. Well, that didn't happen. the thing was just creeping off to the left. And so then I said, okay, if it's, or off to the right rather, if it's creeping off to the right, then it's definitely not going to repeat itself. But maybe it's creeping off to the right in a way that repeats itself. Every 20 it looks like the same but shifted by something. And I can find that pattern and use that pattern. And it turned out it was actually a very simple pattern that after 184 generations, every step it just kept moving. The sum increased by 42. So figure out what the sum is after some number, and then figure out how much has to increase all the rest. So it's kind of cheating, but that's the cheating that that you have to do in order to finish these advent of code problems. So although this is not like an ideal chunk of code, we will add it to GitHub anyway. So let's call this day 12 and git push. Okay, so that is up there now, and okay, so that's good. So as always, you can find me on Twitter, where I will share these videos and complain about the problems and argue with people about Jupyter Notebooks and things like that. And you go to YouTube to see them, but you're already on YouTube because you're watching this, so you don't need me to tell you that. And I have this Patreon that you can check out if you want to kick in some dollars, but you don't have to. That's all right. So anyway, thanks for watching, and I will probably be back at this tomorrow, would be my guess. So cool. Have a good night, everybody, and I will talk